All right. So section 3.2 is on the RSA public key crypto system. Now, RSA it's stands for the initials of the three researchers that invented this algorithm: Rivest, Shamir, and Nadelman. And this is a venerable old algorithm that goes back to 1978. So, what is the description of the crypto system? So it's as follows, right? So let's so description. Let's start with the public parameters. So the first public parameter is an integer n equal to the product of two different primes, just like in the previous lesson. Right? Now, even though n itself is public, the primes P and Q are to be considered secret. Right? So you can reveal, and in fact it's one of the components of the crypto system is n, which is going to be used as the modulus for congruences, but the actual factors of n are to be considered secret. They're not really part of the secret, but you could recover the secret with them very easily and efficiently. So as soon as you can factor n, you can break RSA. The security of RSA depends in a critical fashion on the difficulty or unfeasibility of factoring n, even knowing that it is a product of two distinct primes. The second public ingredient is an integer e, considered as an integer. It has to be coprime to p minus 1 times q minus 1. This is what this really means is that E is coprime to the least common multiple of p minus 1 and q minus 1, as we discussed last time. So this E should be generated randomly and made public. The chances that when you generate a random integer that it is not going to be coprime to p minus 1 times q minus 1, I mean, you can always check. So and that's a key ingredient. Now the private part of the crypto system, it depends on knowing L equals to the least common multiple of p minus 1 q minus 1, as in last time, right? And D equal to the multiplicative inverse of E modulo L. You could do this if you wanted. You could do this with replacing L by p minus 1 q minus 1 and D E inverse mod that L, right? It wouldn't make a difference, but in reality, you're only working with exponents modulo L. The key thing is that to remember here is that neither, certainly L, neither P nor Q nor P minus 1 or Q minus 1 nor therefore L are known. Of course, once you know L, it's very easy to find the private decryption exponent D as E inverse modulo L. That's a very efficient computation. But the point is that we're assuming that it's you cannot really find L. Sorry. All right. So how does the encryption in RSA work? So the messages in ciphertexts are elements of UN, right? Remember that UN is the units of Z mod n. And in fact, I'm gonna make a quick comment. Actually, really, you can take messages in ciphertexts in all of Z mod n, and all of this works just fine. However, if you ever deal with an element of Z mod n that is not a unit, in all likelihood you have actually found a prime factor, either P of Q or N. So that's already a really, really bad thing. And it would be extraordinarily lucky if you were to ever run into a message or a ciphertext that is actually not coprime to N, right? So whatever. So a message, so the encryption, right? Let's go back to the encryption. Right? So it goes given M in UN, so that's the message you're trying to encrypt. So the corresponding C is M to the E. Now let's see if we can make this a little bit prettier. Oh, I'm sorry. Nope. I'm gonna give up on this for now. Well, yeah, sorry. All right, just finishing here. So that is the way you get the ciphertext from plain text. Now the decryption. Oh, I'm sorry. And I should say that this is, of course, all working modulo n using the arithmetic of Zn. So even though the exponent and m and n can be really, really large numbers, of up to the size of n or so, this can be done with efficiently with using fast exponentiation in Z mod n. The decryption to recover back your message is given C. You get back M as C raised to the decryption exponent, and again using arithmetic modulo n. So that's how you decrypt in RSA. So let's prove this. Okay, so proof that this operation, the decryption works. Okay, so again, given M I guess M congruent, I'm sorry, that the the ciphertext is congruent to M to the E modulo N. So let's just consider M tilde to be C to the D modulo N. So what we need to show is that M and M tilde are really the same thing in Z mod N, right? So then we have this this chain of congruences, right? So M, right, which is congruent to C to the D, is actually congruent to M to the E to the D, right? Which is of course M to the ED. All of this is modulo N, right? But here's the key thing, that M to the ED is congruent to M to the 1, which is equal to M. And the reason behind this is the key to understanding the structure of Z mod N that helps this be true, right? The reason is that every element, let's just say every element X of UN satisfies X to the L is congruent to 1 modulo N, correct? So this is the fact that every the exponent of the group UN is equal to L, right? Where L is equal to the LCM P minus 1, Q minus 1. This is still true if you replace L with just the product P minus 1 times Q minus 1. This is still true, simply because this is a divisor. The divisor, P minus 1, so P minus 1 times Q minus 1, right, is a divisor of the least common multiple of P minus 1, Q minus 1. So, but that's not a major thing. So because this magic exponent has the property that that's the exponent when you get back to X to the 0, right? X to the L is the same as X to the 0. So this implies that X to the A is congruent to X to the B when A is congruent to B mod L. Of course, this is mod N. So the congruences mod N are respected by changing the exponents, right? If you change the exponents modulo L, then the congruence modulo N of the powers are respected. And that is the end of the proof that RSA works.